So welcome to our tutorial today. We'll be talking about instance-level visual recognition. I prepared a really nice introduction, but for the interest of time, I'm going to skip it. So, okay. But briefly, I just want to say that I want to make clear what we mean when we say instance-level visual recognition. So the goal is to understand and recognize all objects in the scene. And this can take many different forms. One is, for example, we might want to just place a tight box around every object in an image. This is what you know as object detection. But it can also take other different forms. For example, you might want to predict the spatial support for every object, which is instance segmentation. Or even more fine-grained than that, you might want to predict the pose of every object. This is predicting the position of landmarks of objects, what we call pose estimation. And of course, you might want to predict a lot more things, such as interaction between objects, or also even predict the object's behavior in time. So today, we have a wonderful set of speakers that will cover almost all of those topics. And we'll start off with Ross, who's going to present his talk title is the Generalized RCNN Framework for Object Detection.
Don't applaud quite yet. I don't know if we'll actually get the next slideshow running. All right. Can everyone hear me? So it's a little awkward sitting down. I had expected to be able to point to stuff, but I don't think I'll actually be able to do that, but that's okay. So what I'd like to do today is present several topics, and there's a lot of stuff in here, and I'm not exactly sure if I'll be able to get through all of it in time, but hopefully, so let's dive right in. So just to introduce object detection very briefly, the problem is typically formulated as predicting a bounding box, so that you can describe both what is in an image and where the things are located in an image. So for example, the output of an algorithm might look something like this, where you have the scene and there are people and a boat, and if your algorithm works well, it will correctly identify and localize these objects. So let's get a view of how well object detectors are working today. So one way to do this is to look at how systems perform on the benchmark Microsoft COCO object detection data set. So we can take sort of a historical perspective and look at one of the best methods before deep learning sort of took over the field of object detection. So that's the deformable parts model, this DPM over here. And if you were to take that algorithm and run it on COCO and benchmark it, you get somewhere around 5% average precision. Now, when deep learning sort of revolutionized object detection after sort of one generation of methods, that number suddenly jumps up to 15%, sort of a 3x improvement in object detection. And at the time, that seemed like this sort of amazing improvement. But what I'd like to show you is that sort of, to me, what's even more amazing is that this 3x improvement has actually replicated itself again. And over the last 2.5 years, we've seen this number of 15% become what is now about 46%, or maybe we'll even learn later in this week at the COCO workshop that this number is even larger. So this is really kind of the result of several factors. I'd say that the two most important factors are the continued development of better sort of backbone convolutional networks that are typically first trained for image classification. And the other factor is the design of better object detection methods and then the tuning of those systems over time. And what I'd like to focus on this tutorial is that latter part, the design of better object detection systems. So developing a whole bunch of different systems by a lot of researchers in this community. And what I want to do right now is kind of present one strand of that research, which has been on this RCNN framework. And I want to sort of provide a slightly different perspective than people have probably seen in the past, which is to show it in sort of one generalized or unified view or framework. So during the development of this, I'm going to be putting up these slides that are sort of like a title slide introducing the name of the system. And there will also be a list of references. And I don't have the time to go through all these references in detail, but the slides will be available offline, and you'll have a chance to see sort of what the referred papers are as kind of a reading list for this material. So let's start with an overview of RCNN, which stands for Region-Based Convolutional Neural Network. So this is an object detection system that, roughly speaking, divides computation into two parts. So there's a per image computation that's done once on the whole image. And then, as you'll see in a moment, there's a per region computation. So let's start with the per image part. So it starts with taking an off-the-shelf region or object or detection proposal algorithm, such as selective search, edge boxes, MCG. There are dozens or maybe even 50 of these by now. And the output of such a system is a set of, say, 2,000, that number is usually a hyperparameter, of proposed places in the image where objects might appear. Now, the idea is that these are not actually high-precision localized objects, but just that it's a set which should contain any objects that appear in the image, so it has high recall. Now, given each one of these locations, there's a per region computation, which in RCNN involves cropping out the image window underneath the proposal, warping it to a fixed canonical size, which can then be fed through a convolutional network in order to produce a fixed length feature vector that describes that region. And then that feature vector can be passed to one versus rest SVMs for doing the object classification, and a bounding box regressor whose job it is to take the original proposal and deform it so that it hopefully better matches the actual spatial extent of the object that's being detected. Now, there's a big problem with this approach. And the problem is that the amount of computation that's done per region is actually extremely heavy. And what this leads to is doing, say, 2,000 full neural network evaluations for a single image. And that's going to take anywhere from a few seconds to several minutes, depending on the size of the neural network that's being used. So I now typically refer back to the system as sort of slow RCNN, in contrast to the subsequent methods. So what I want to do now is present faster, and then a modified version that uses a feature pyramid network versions of RCNN, but I want to do it within sort of a common unified framework that will hopefully make it easier to understand how all these methods relate to each other. So what does this generalized framework look like? So it has the same division of a per image computation and a per region computation. Now, the first part of it is this abstracted box which has some function f, which is going to convert the image into a featurized representation of that image. And then there's some other function r, which takes the image and converts it into a set of these region proposals. And then there's some other function that's abstract and not specified, g, which for each one of those regions is going to take that region together with the featurized representation of the image and convert that region into a feature representation. Then there's another function that does some processing on it, and then there are several heads of the network which perform task-specific predictions per region. Okay, so with that view in mind, let's take a look at how fast RCNN is instantiated in this framework. So the first step is that this function that transforms the image into some representation is going to be a fully convolutional network. The second part is that there's going to be this region of interest pooling operation, which is going to extract out region-specific features from this full image feature representation. The subsequent processing on that is going to be a multi-layer perceptron, and then the task-specific heads in this case are going to be a softmax classifier over background and the different object categories that exist, and then a bounding box regressor that again is going to deform the proposal into a new rectangle that hopefully actually matches the spatial extent of the object in the image. And to relate this to previous work, FastRCNN can be viewed as sort of an end-to-end trainable version of Kai-Ming's SPP net. And the sort of main innovation in FastRCNN compared to the previous work is to make it both end-to-end trainable and also keep the per region computation pretty low. So I want to dive into two parts of this system in a little bit more detail. So the first is the FCN that converts the image into a feature representation. So this can be any standard ConvNet, and we typically refer to it as the backbone architecture. So for example, this could be AlexNet, VGG, ResNet, Inception, ResNet, ResNext, DenseNet, and so on. This is sort of a modular part of the system. But each of those backbone networks is typically pre-trained on ImageNet, and in order to convert it into a fully convolutional network, a little bit of surgery has to be done. And usually that involves simply replacing any sort of global pooling or fully connected layer that exists in the network. And the thing to note here is that because this is a fully convolutional network, it's going to produce an output feature representation which has dimensions that are proportional to the input dimensions. And then I just want to sort of emphasize again that going back to the graph I showed at the beginning of this talk with the improving performance of systems over time, there's a good chunk of that performance improvement that can be directly attributed to the development of these better networks. And so this sort of goes back to the first line of the RCNN paper, which is to say that features matter because good networks have the property that they sort of lift all boats, where boats are tasks in computer vision, and specifically object detection has benefited enormously from these advancements. So now the second part of the FastRCNN system that I want to dive into is the ROI pooling operation. So ROI pooling is an operation that was introduced in the SPP net system, and its job is going to be to take each of the region proposals and figure out how to extract region-specific features from the feature map computed by the FCN. So the first thing it will do is it will project the region into the feature map. And then it's going to quantize it from whatever floating point coordinates you have to ones that actually snap to or align to the underlying feature map. And then, because all the subsequent processing is going to involve operations that require a fixed size input, it's going to perform an operation that coerces this arbitrary sized region into one that has a fixed size. And the way that that's done is that when the proposal was projected and quantized, it was divided into a grid. And say that we want to get a 2x2 feature representation out of this, then what happens is that for each one of these bins in the output, you go back to the corresponding bin in the input and do max pooling over the elements in that bin. And then this produces a fixed size representation which can be subsequently processed by, for example, multi-layer perceptron. Now, there's a problem with FastRCNN as well, and it's largely that this box over here, which has the region proposal part of the system, is still sort of an off-the-shelf, handcrafted system that's not able to learn and adapt to new data distributions. And what we saw during the transition from the Pascal VOC dataset to the COCO dataset is that while these methods seem to work pretty well in Pascal in terms of having high object recall, when you move to COCO, they suddenly became a major bottleneck of the system. They were consistently missing all the small objects and causing the performance of the overall system to remain low. So the idea of faster RCNN is really to replace this hand-designed part of the system that was not trained, or at least didn't have many trainable parameters, with one that was able to learn how to find objects based on the data set that's given. So faster RCNN is really about addressing that box down here, which is now highlighted, and replacing it with what's called a region proposal network. And the region proposal network sort of has two important properties. The first is that it can propose where to look in the image to find objects. And the second is that it's actually going to share the feature representation that's computed by the FCN, which is why I've changed this arrow here to sort of point down from this feature representation here down to that box. And this enables the computation to be very fast because the marginal cost of running this region proposal network is going to be quite low. So let's take a look at what RPN does and how it works. So RPN uses sort of a 3x3 window of analysis when it's looking for objects. And it runs in a sliding window fashion. So as it moves along the image, it's going to scan looking for objects. And the way that it predicts whether objects exist and where they're located is not based on the 3x3 window itself, but instead it's abstracted so that the predictions it makes are relative to what's called an anchor box. So the anchor box can be larger than 3x3, smaller, different aspect ratios. And so the important thing to note is that the predictions are going to be relative to the anchor, not the 3x3 window. And in particular, for each anchor, it's going to use an objectness classifier to predict whether or not the anchor corresponds to an object. And it's going to have a bounding box regressor, which will deform the anchor to match the spatial extent of the object. So here's an example. If the 3x3 window of analysis is centered on some object, what should happen is that this anchor should be given a high probability of being an object by the objectness classifier. And the original anchor box, which was the square, should be deformed by the bounding box regressor so that it matches the extent of the object that it's detecting. And now here's another example where the window of analysis has scanned over so that it's now on the foot of the object, and the anchor box no longer corresponds very well to the object. So what we'd expect is that the objectness classifier should give it a low score, and the bounding box regressor could really do anything because it doesn't matter because the objectness score is low, but in reality will most likely predict something close to identity transformation. Now, the advantage of using this idea of anchor boxes is because it decouples the prediction from the 3x3 window of analysis, is that you can now have multiple anchors associated with each sliding window location. And so here, what I'm depicting is a set of 3 anchors which have different aspect ratios in roughly the same area. So now, for each location, there are going to be k objectness predictions, where k is 3 for the 3 anchor boxes here, and there'll be k box regressor predictions to deform each of those 3 boxes. Okay, so that explains the region proposal part of the system. Now I want to describe some more recent work which replaces the single scale output from the fully convolutional network with a feature pyramid that's output by a feature pyramid network. And the reason for doing this is to make the network better at handling objects that range over a variety of different scales. So, as I was just mentioning, detectors basically need to perform 2 things. One is to classify objects that are there, and the other is to localize them. And they need to do this for both very small objects and for very large objects. And the goal of the feature pyramid network is to improve the system's invariance and equivariance to scale transformations. So I'll go over 4 strategies for accomplishing this, one of which is FPN. So the first strategy is the very classical image pyramid approach that's been used since probably nearly the beginning of time in computer vision. And the idea here is that you form an image pyramid, and then for each level in that image pyramid, you probably have some feature transformation of it. So for example, that could be hog features or a convolutional network that's run on each level of the pyramid. And then the system, in this case an object detector, will make predictions from each of those levels of the pyramid. Now, this is a very good solution in the sense that it still tends to lead to the most accurate final system, but it has a disadvantage of being quite slow because there's a lot of computation that has to be performed independently for each of the levels of the image pyramid. Now, the second strategy is to kind of push all of the work into the features themselves and just say that we're not going to worry about having an explicit representation of scale in the system. It's just going to get stuck into the features somehow. And this is what a lot of more recent object detection approaches have done. And so in this figure here, you should interpret this as this image here goes into a neural network, which is downsampling the image a few times while it's processing it. And then it has some final single-scale feature map representation here, which is then the basis of all the predictions. And the regions of interest will get mapped to different sizes in this single-scale feature map. And small objects will have to be handled by specialized features that are good for classifying small objects, and large objects have the same story. Now, this is fast because you don't have to do individual processing for different levels of an image pyramid, but we know that it's suboptimal because the image pyramid version of the system is always going to outperform this version, at least from what we've seen so far. So now there's probably something that you noticed along the way, which is that the convolutional neural network is producing different resolution representations as it's processing the input. So one thing that you could try to do is take advantage of the sort of inherent in-network pyramid that's being computed and to make predictions from each of those levels of the network. So this is going to be basically just as fast as the previous method that I showed you. But again, it's going to not be as good as we can do. And the main reason for that is that if you look at sort of the strength of the features in terms of how able they are to classify objects, what you end up with is that at the low resolution feature map, it has very strong features. But at the low resolution feature map, it's going to have weak features. And these are, depending how far down you go in the network, possibly going to be features that correspond to edges and texture. Features that are not typically very useful for classifying objects. So the idea of the fourth strategy, which is the feature pyramid network, is to build a U-Net-style convolutional network that has sort of an up pass and a down pass, but then to use each of the feature levels that's computed in the downward pass as the basis for making predictions about whether objects are in the image. And this is going to be basically just a little bit slower than the previous methods because the amount of computation that we're doing in the downward pass is very lightweight, and it's going to be less suboptimal. And the reason why I say less is because what we found is that if you combine this approach again with the image pyramid approach, you still see improvements. So while this does take a step in the direction of improving scale, invariance and equivariance, it doesn't fully alleviate the issues. So let's take a look at what one of these top-down refinement modules looks like. So it takes an input from above, which is the previous feature map of the pyramid. It does a 2x2 nearest neighbor upsampling. We found that it doesn't particularly matter whether you use nearest neighbor or, say, a learned conv transpose upsampling. We use nearest neighbor simply because it's fast and doesn't seem to make much difference in practice. And then it's going to take in a lateral input from the first part of the upward pass, or the first part of the full feed forward approach. And it's going to have a 1x1 convolution, which is going to project the feature dimension down into one that's compatible with the feature dimension of the pyramid. And then it's just simply going to sum those up. And then this procedure repeats recursively from the top down in order to fill out the feature pyramid. So this has the advantage of propagating the strong features from the low resolution down to the high resolution features while combining them in a way which is able to maintain strong features at a high resolution. And I just want to mention that this idea of using a feature pyramid network is a fairly generic modification to the backbone architecture that's being used. So we've found that it's useful in a variety of applications. So for example, it greatly benefits region proposal networks. We use it in fast and faster RCNN. It's also quite important in Nascar RCNN. Kai-Ming will be talking about this in the talk that we have on Thursday. It's also the basis of the Retina net one-stage detector, which I'll talk about a little bit later today, and it's also another talk on Thursday. And then we have a semantic segmentation system that's built on FPN, which will be presented at the COCO workshop on Sunday. So to summarize the first part of the talk, it's really that there's been a lot of progress in object detection, and that progress has come through the development of these better object detectors, which are really incorporating a lot of domain-specific knowledge. You'll notice that they aren't the result of just sort of like a very generic black box design. It might be nice to be able to do that someday, but at the current state of things, it's not possible to get these state-of-the-art results by just kind of throwing in the problem into kind of a generic system that's able to learn how to do everything. It really benefits from having object detection domain-specific ideas built into it. Okay, so now I want to move into the second part, which is a bit shorter, and that's going to cover one-stage versus multi-stage detectors and also a related topic of speed and accuracy trade-offs. Okay, so what is this idea of stages and why do we need them? So if we take a look at the object detection problem sort of in the abstract, so if you have a pixel with n images, sorry, if you have an image with n pixels, that's going to lead to on the order of n squared boxes, which is essentially the output space of the object detection problem. So this is huge. Even if you have a really small image, say like 300 by 500, this is going to lead to billions of boxes that exist in the image. Yet the number of objects that we're trying to detect in an image is a small number, say 10. So this leads to a massive imbalance between foreground boxes and background boxes, which don't correspond to any object. So how do we deal with this problem of class imbalance? Well, there are really two strategies that have been developed in the literature that have been very successful. So the first is just this idea that you're going to really drastically subsample this output space while maintaining high recall. So most of these billions of boxes in a small image are very similar to each other. And in particular, if we're using a method that has some sort of bounding box regressor in it, it surely isn't necessary to explicitly consider each and every single one of them. So this is something that people observed a long time ago, and there have been two successful approaches, at least, for subsampling the output space. So the ones that come to mind are sliding window, in which a small set of sort of discretely sampled spatial locations, aspect ratios, and scales are chosen to cover this large space. And then the other approach, which has become sort of more common and more popular over the last few years, is the idea of using object proposals, which are sort of, you can think of them as sort of a data-driven version of sliding window. So rather than having a regular sampling, like the sliding window approach, the object proposal approach says, let's look at the actual image data and then decide where to look based on the image content. And I guess I should just mention that as you saw in the RPN system, these ideas sometimes end up kind of intertwining with each other because RPN is fundamentally a sliding window approach. It's just being used to generate proposals. So now the second strategy for dealing with class imbalance is the idea of using a cascade of stages. So probably the most famous example of this is the Viola-Jones detector. So that detector used a boosting algorithm in order to develop a staged cascade classifier in which every stage is deciding whether to accept or reject possible objects. Now, this is very typically combined with subsampling, such as sliding window. And I just want to note that the idea of subsampling itself is already sort of an implicit zeroth stage of a cascade because it is already making a hard decision about whether or not different elements of the output space should be considered. So let me show an example of a two-stage system using proposals via the generalized RCNN framework. So the first stage is the proposal mechanism itself is going to eliminate most of the output space. And then the second stage is to simply classify whatever proposals remain. Now here's an example of a one-stage system. In the one-stage system is, in this case, Yolo is going to use a drastic subsampling of the output space. So for example, it's going to consider only 98 out of billions of boxes and directly classify for each one of them whether they're the object or not. So the view to have here is that class imbalance is really the central sort of learning challenge for object detectors. And one-stage systems have typically addressed this via either subsampling the space dramatically. So for example, Yolo that considered 98 boxes, the second version that considered about 1,000, Overfeet, which considered roughly, I think, around 1,500 boxes, and SSD, the single-shot multi-box detector, which considered somewhere between, say, 8 and 26,000. And as you move from these very small number of boxes to more boxes, what happens is that this class imbalance problem becomes more and more dramatic, and there's a need for additional machinery to come in. And so for example, hard example mining is one of the strategies that's been used, for example, in SSD in order to help deal with this imbalance in a one-stage system. Now, I want to briefly go over Retina Net, which I think is a one-stage system that's a little bit unique compared to the others in the sense that it's able to perform this one-stage object detection while considering a very large number of candidate objects. And that's going to enable it to achieve results that are comparable to that of two-stage systems. And so the key to enabling that is via the development of a new loss function for training it that's able to deal with the class imbalance. So the model architecture for Retina Net is very basic, and the idea is not to propose something novel here. So basically it's just going to be your favorite backbone plus feature pyramid network, and then what can be viewed as a class-specific region proposal mechanism that's going to output the final detections. And that part of the system is going to use 6 anchors per location in the pyramid. So there'll be 2 scales, and for each scale there'll be 3 aspect ratios. And this is going to lead to, depending on the size of the input image, between, say, 100 and 200,000 anchor boxes to classify. So sometimes we refer to this as dense detection because compared to other one-stage systems, this is a very dense sampling of the output space. And now the key to making this work is the development of a loss function that's effectively sort of a soft version of hard example mining. And it's something that we call focal loss, which I'll explain in a moment. So this graph here shows the loss functions as a function of the probability of the ground truth or the target class being predicted. So the outermost curve here that's in blue is standard cross-entropy loss for binary classification. And the thing to note is that for examples that are even reasonably well classified, say 0.8, maybe 0.9, this loss function actually has considerable non-zero loss associated with those examples. So that means that in this sea of thousands, hundreds, roughly 100,000 negative examples in an image, even if those have predictions that are pushing up into 0.99, say, they have a large enough loss associated with them that in aggregate, they produce a large amount of loss. So the idea of focal loss is to focus the loss on this part of the curve. And the way that that's happened is via this gating or modulating factor out front, which basically says that if an example is well classified, if gamma, the power here, is greater than 0, then you should really push down on the loss for that example. So in practice, what happens is if we compare a Retina Net system that's trained with cross-entropy, it gets around 31% average precision for this particular model configuration. And now if we introduce this focal loss and with this gamma parameter and tune it into this regime where it performs well, say gamma equals 2, then that's able to produce about a 3-point average precision improvement. And here are sort of some quantitative plots in order to sort of justify this description of it being a hard mining mechanism. So what these plots show is, as a function of the fraction of examples considered, what's the cumulative loss associated with those examples. And you can see from the plot on the left that for foreground boxes, there isn't a huge difference between cross-entropy, the blue curve here, and focal loss with gamma equals 2, the purple curve down here. But for the background boxes, as you move from cross-entropy, which really spreads out the loss amongst a lot of different locations, to focal loss, with focal loss, you end up having almost a delta function on a very small set of boxes, where all of the easy ones are given a very negligible amount of the loss. So this sort of produces in a soft way a hard mining type behavior. So now I want to briefly transition before wrapping up to a related topic, which is that of speed accuracy trade-offs. And this often comes up in the context of 1 versus 2 stage detectors. So here's a plot showing inference time in milliseconds versus COCO average precision. And this plot has a variety of methods. So many of these are one stage, so like Yolo, SSD, deconvolutional SSD, some other variants of SSD with different input sizes. And then it has a 2-stage system, fast RCNN using feature pyramid networks. And then the connected curves here show 2 different versions of RetinaNet using a ResNet 50 and a ResNet 101 backbone with FPN. And this is showing that as you change the size of the input, that you trace out this curve for each one of these networks of different points of average precision versus inference time. So these trade-off curves are really a function of the flops being performed by the network. The more flops you compute, the slower it is, and the higher the average precision. But there's sort of a big caveat that I want to give along with graphs like that. And that is that for the most part, there are some exceptions, these comparisons in the literature are completely uncontrolled. They're, in the case of this plot over here, taking reported numbers from different papers and throwing them onto the same plot. But really, there's a lot of different factors that can affect the speed of these systems and the accuracy for that matter. So for example, the amount of tuning that's gone into low-level optimization of all the different ops, whether there are some specific test time tricks that are being used in order to make inference faster, such as batching inference. And then the other thing is that there are lots of hyperparameters associated with these systems, or small design decisions that are sort of below the quantum of a publishable paper. And these sort of components of the recipe often greatly change where something will land on this plot. So for example, if you were to take this point G and then make some improvements to say like the training schedule, the particular region of interest pooling operation that's being used, maybe optimize the non-maximum suppression threshold a bit, train it with end-to-end training, then for example, that could shift this point up here, and not just can, but does. So the point is that in any sort of plot like this, there's a lot of noise in these comparisons, and you should always take these with a grain of salt. So to summarize these points on fast detectors, in my view, the key design decisions about making a detector fast are all about how do you reduce the flops. Making the input resolution low, making the backbone network lightweight. If it's a sort of 2-stage proposal-based system, using a small number of proposals, say 10 to 50, which is often enough to get like 90–95% of the total possible AP out of the system. And then there's sort of an anti-factor, which is this sort of coarse-grained description of 1-stage versus 2-stage, which really is not the underlying thing that's just determining whether the system's fast or not. It's more about these other factors above. So in conclusion, there are 4 takeaway points that I'd like you to leave this with. So the first is that object detection isn't solved. There still are a lot of challenges left. There's been dramatic improvements on COCO, but even in the world of COCO, if you actually look at completely random images with visualized results from the best systems, you'll see lots of obvious mistakes. And even if COCO were solved, these data sets at the end are just models of the world. They're toy models of the problem. If we think we've solved one, that probably just means that we need to develop a better model of the actual problem we're trying to solve. The second point is that features matter. They still matter. The development of better backbone networks continues to drive the improvements in a lot of different tasks, including object detection. The third is that detector design matters a lot. And a lot of the progress that we've seen over the last several years is the result of applying some domain-specific knowledge in object detection to the design of better object detectors. And then the last point to leave you with is that speed and accuracy is not just a single point. It's not a question of, is YOLO better than SSD? Is SSD better than X? One should really think about these things sort of more broadly in terms of the speed-accuracy trade-off and the fact that this is sort of a curve or more generally a surface. So with that, I would like to conclude, and I think we're probably almost out of time, but maybe 1 or 2 questions. I didn't quite get the first part of the question.
For the top-down passport and the lateral connection, in the future pyramid network, is that from the experiment or it's like any intuition?
Oh, okay. So the question is, what's the intuition behind the future pyramid network design? That was largely driven by the intuition that you want to have strong features at multiple resolutions because we know from image pyramids that you can get better results by having a multi-scale representation. And so the intuition just seems that you should be able to take the strong features at low resolution and merge them in some way with the higher resolution, weaker features. I mean,
If it's wide nearest neighbor and the loss from the lateral.
oh, yeah, so I mean, that's just an empirically validated thing. Initially, we thought nearest neighbor probably wouldn't work as well as, like, say, bilinear upsampling or a learned version. It just empirically, it does work as well. And it's fast, so might as well do that.
There was like very small detections in the stream and in the like traffic scene that are far away. None of these methods were really working properly because all these images are downsampled. I don't know if this is also covered without hard negatives or not.
Yeah, so the question's about small object detection, and I guess why it still doesn't work very well. Yeah, so performance on small objects continues to be much worse than on sort of medium and large size objects. One of the initial motivations of future pyramid networks was to address that to some extent, and it did bring fairly large improvements in small object detection, but obviously it's still not completely solved. I think that actually to some extent we're limited by the data sets. Most of the data sets we work with still have very low resolution images in them, say like 300 by 500 pixels. So to some extent it's an artifact of that. I think maybe we need to move to the next speaker now. But all right, thank you.
So next up is Kai Ming, and he will talk about Nascar CNN, a perspective on equivariance.
Okay, so I'm going to talk about mass RCN. And by the way, so this logo is a Venetian mask. So I think Venice is a very good place to present this work. So a little bit background. So there are many visual perception problems being solved nowadays. So but in my opinion, these are the 3 most important problems. One is object detection, and another is semantic segmentation. And actually, both of these problems have been, improved by a lot in the past few years. On the other hand, instant segmentation, which require to both detecting the object and then segmenting them has not been improved so much in the past few years. So here is one of the data points that can show that instance segmentation is still a challenging problem. So if you count the number of entries in the COCO leaderboard, you can see there are over 30 object detection entries, but there are only 5 instance segmentation entries. And if you see the cityscape leaderboard, for the semantic segmentation task, there are about 60 entries. But on the other hand, there is only 11 instance segmentation entries. So this number shows that it is still a very challenging problem for instance segmentation. So in my opinion, why object detection or semantic segmentation have been so popular in the past few years? One of the reasons is that we have very good systems as kind of a meta algorithm for these problems. So in the case of object detection, one of the meta algorithm is the very successful fast and faster RCN system. This system has good speed and most of the times very good accuracy. On the other hand, these systems are very intuitive and they are easy to use. So by easy to use, I usually mean they are both easy to train and also easy to test. And also it is easy to do experiments on top of them so we can accelerate the research cycle. And we have the same story on the semantic segmentation task thanks to the fully convolutional network meta algorithm. So actually, in my opinion, since the development of FCN, almost all the semantic segmentation methods are kind of FCN. And also FCN have good speed, good accuracy, and it is intuitive, so it is easy for people to use and do research on top. Then actually the goal of mass RCN is to play such a role for the application of instance segmentation. We expect we can propose a meta algorithm which has good speed, good accuracy, and which is also intuitive and easy to use. So in the past few years, there are a few methods for instance segmentation, and these methods can be roughly categorized into 2 families. One family is driven by the success of the RCN system. So basically, these methods will first start from some segmentation level proposals such as MCG or the segmentations from selective search. And then they will run kind of slow or fast RCN to classify these proposals into instance segmentations. And another family of methods are kind of FCN driven. They usually start from the semantic segmentation result, which does not distinguish the object instances. And then starting from this result, they try to kind of cut this semantic segmentation results into separate instances. So here is a very rough categorization of the methods in the literature. So SDS, also known as simultaneous detection and segmentation, is possibly one of the first RCN-driven method for this task. So following that work, there are the hypercolumn method and also the convolutional feature map masking and multi-stage network cascade methods from MSRA. So these methods are kind of the RCN-driven methods. And on the other hand, for the FCN-driven methods, it is pioneered by a paper called Proposal-Free Network. And in this CVPR, we also see the papers called Instant Cards or Watershed, which are driven by the FCN output. There are some other methods that lie in between these 2 families. For example, FCIS or DRM, which starts from the kind of an FCN network, but also started to exploit region proposals. So in this context, actually, mass RCN is very simple. So mass RCN is just no more than a faster RCN system for object detection, which has fully convolutional network applied on each of the ROIs. And basically that's it. One of the most important behavior of mass RCN is the parallel heads for the three tasks of classification, bounding box regression, and mass prediction. So if we go back to a few years ago, let's think of how we go from slow RCN to fast RCN. So there are many innovations in the fast RCN system, but in my opinion, one of the most important one is that it combines the task of classification and bounding box regression into a multitask loss problem. So actually, in the original slow RCN system, it is a two-step system. In the first step, you learn to classify the region proposals, and after you get this classifier pre-trained, you again train another bounding box regressors on top of it. So when we move from slow RCN to fast RCN, we combine these two steps into a single network, and it is just two tasks and two laws of the same network. So in my opinion, mass RCN is in the same spirit of this multitask learning. We have three tasks, one for classification, one for bounding box regression, and the other is just for masks. And all these tasks are in parallel, so they share the same features, and they can share the same region of interest. So it is very easy and very fast to implement. So basically, these are some background of mass RCN. And in this talk, I would like to tell a story which I did not tell in the mass RCN paper. And it is just some random thought, but I think it is an interesting story on the perspective on equivariance of mass RCN and the problem of instance segmentation. Now let's stop for a few seconds and think about this problem. So how can we draw the Apple logo? So by the Apple logo, I mean the logo of the Apple company. So these are what people draw when they cannot see the Apple logo. They just draw this from their memory. You can see that there are many different types of results. There are some red apples. There are some apples without a bite. There are some apples which bites facing left or facing right. So this is the ground truth. So some of the people did a very good job, but most of the results are not as good as what we expected. Then let's think about this problem again. Now let's think about what is given to the person who will draw the Apple logo and what can be drawn. If the person is given nothing, he has to draw the apple from his memory and he's only given a blank paper, then maybe this is the best he can draw in terms of the Apple logo. So it is not too bad. It is an apple. It has a bite, but actually it is not the Apple logo. Can we do a better job? So if you are the person, maybe you will ask for a ground truth as a reference. Now, if I let you to see the ground truth, but I still give you a blank paper, then it depends on your skills of drawing. The apple may look better. So for example, it is an apple with a bite on the right, and maybe it has a leaf on the top. But still, you can see that it is still not the Apple logo. So to do a better job, actually, you may want to do something like this. You may want a semi-transparent paper, and you may want to have an Apple logo as the reference. And then you impose your paper on top of the reference, and then you can use your pencil to outline the reference. And I think this is the best way for you to draw the Apple logo. And in this case, it is pixel to pixel aligned. So I think this can roughly describe how we go from an object detection problem or maybe an object recognition problem to an instance level segmentation problem. In the instance level segmentation problem, we not just want an apple. We not just want an apple with a byte. Actually, we want the apple. We want the apple that is pixel to pixel aligned with your ground truth. So here comes the discussion of invariance versus equivariance. So usually invariance means that you are given some different input, but they have the same output. So for example, in the first example, you are given two apples, and then we have the classification label, which is just called apple. So the label of apple is the invariance of this example. And in the second example, actually we can have a slightly more fine-grained invariance. For example, people can say this is an apple, and this apple has a byte on the right. But still, it is still kind of an invariance. Then what is equivariance? So equivariance means if you change the input by some transformation, then your output will be changed by more or less the same amount of transformation. So for example, in the problem of semantic or instant segmentation, if you translate your object by some offset, actually you will also like to translate your output mask by the same amount of shift. So in this case, actually invariance is not what you want. You need equivariance. So another example is that you may also want some scale equivariance. So if you scale your object by some amount, then you may also want to scale your output by some amount. So more formally, as I mentioned, equivariance is that if you change the input, then you may also want to see the corresponding change in the output. And in this context, if we rethink the instant segmentation problem, you can see that actually instant segmentation is kind of an equivariance problem. It is not like classification, which just need an output, so which can just be an invariant problem. So in the case of instant segmentation, if you translate the object, you want to translate the mask. If you scale the object, you also want to scale the mask. And also, more importantly, if you have a big object, you have a small object, they are equally important. This is because how we compute AP metric. The AP metric is based on the IOU score. So this property is unlike the case in semantic segmentation, which you simply count pixels. So usually in the case of semantic segmentation, big objects are more important than smaller ones. So all these properties in instant segmentation require kind of equivariant representations in our system. So actually, the convolutions as a single layer, not as an entire network, are by design translation equivariant. So if your network is fully convolution, then your entire network is translation equivariant. But usually a classification-based convolve net becomes translation invariant because it may either have some fully connected layer or it may have some global pooling layer which remove the position information. So after the fully connected layer or the global pooling layer, the convolve net become translation invariant. Then next, I'm going to discuss the equivariance which has been built in the mass RCN framework. So the first very simple equivariance is just caused by the fully convolutional feature maps. So fully convolutional feature maps are kind of standard nowadays. You can see it in almost all the object detection systems such as fast RCN, faster RCN, RPN, SSD, or FPN. So it just means if you translate image globally, you will have the feature map translated globally. And in the case of Marcian, there is another degree of equivariance, which is the fully convolutional layers applied on the ROIs. So this means the mass Marcian system introduced some equivariance into the translations within the ROIs. So let's consider this example. We consider two different ROIs in the same image. One is shown in the yellow box, the other is shown in the red box. So if we describe the mask with respect to these two boxes, you can see that actually the mask has been shifted by a small number of pixels within this ROI. And if you use a fully convolutional network on top of this ROI to predict the output, you may expect the output to be more or less the same if we ignore the paddings and the different contents introduced by the different pixels in these two regions. So this means that if we use a fully convolutional network on the ROI to predict the mask, then it is more robust to small local translation of the ROI, and it may tolerate more localization imperfection introduced by the detection system, including both the bounding box proposal or the object detection bounding box regression result. So this is one nice property of the mass Marcian FCN head. And also, in the case of mass Marcian, we have proposed the ROI align operation, which can introduce more degrees of invariance in the system. So on one hand, the ROI align layer can maintain the translation equivariance before and after the ROI layer. So as I mentioned before, before the ROI layer, the full image shared feature maps are translation equivariant, and the FCN output after the ROI pulling, after the ROI layer, it is also translation equivariant. So to make the entire system to be kind of translation equivariant, we also want the ROI operation to be translation equivariant. So here is some implementation detail of the ROI align. Actually, it is very simple. On top of the feature map, we are given an arbitrary size ROI, and then we just don't do any quantization. We just do bilinear interpolation to sample the points we need, and then we can turn it into a fixed dimensional representation. So there are some frequently asked questions such as how to sample the grid point in the cell. So in our implementation, we just regularly sample 4 points in each cell, and which means each cell is divided into a 2x2 subcell. But actually, in my experience, many other implementations could also work more or less the same. The only important factor here is just that we cannot do any quantization. So this is a conceptual comparison between ROI and ROI pool. So ROI pool actually breaks the pixel-to-pixel translation equivariance, even though it can be just a very small bit, but it depends on how big the stride is in the feature map. It can significantly impact the result. And also, recently, I just noticed there is a talk given by Jeffrey Hinton, which title is "What is Wrong in Convolutional Neural Network?" And actually, in that talk, what is wrong is exactly the pooling operations in convolutional neural net. And in the case of mass Marcian, we have the same observation, and we replace the ROI pooling operation with the ROI align one. Also, actually, the ROI align operation also introduced some scale equivariance, which may also imply aspect ratio equivariance. Now, in the case of instance segmentation, let us think about objects of different sizes and different aspect ratios. So actually, in order to have a good representation, what we want to do is to normalize the representation with respect to the ROI box. And by doing this, actually, we hope it may give us some invariant representations. So for example, for the illustration here, we have 3 apples of different sizes and different aspect ratios. And to do a better job, we may want the underlying representation, for example, the ROI aligned output, to share some common representations that is invariant to the scale and aspect ratio. So this means that ROI aligned creates scale invariant representations. And usually when you have the predictions with respect to your ROI, and then you may want to paste back this output into the original image. And if you think ROI align and the paste back process together, then it can provide some scale equivariant feature or representation for your problem. So regarding the scale invariance, if we apply the ROI align on the raw pixels, which just means that we crop the image and we warp the raw pixel in the image to some fixed size, actually this process becomes the slow RCN style. And if you operate on the raw pixels and if you ignore the bilinear interpolation artifacts, and then ROI align is naturally scale invariant if you consider the ROI representation. However, in the case of fast RCN or mass RCN, we apply the ROI align operation not on the raw pixels, but on some feature maps. So if we want the ROI align features to be scale invariant, then we have to find some scale invariant features. So in our implementation of mass RCN, we adopt the feature pyramid network, which can approximately create some scale invariant features. However, this can also be done by image pyramid or many other scale invariant strategies. So in summary, here are the equivariances that has been considered in the mass RCN system. So the mass RCN system is translation equivariant in terms of the full image, fully convolutional features, and also in the per ROI FCM mass hat. And this is also enhanced by the pixel-to-pixel behavior of the ROI align layer. And on the other hand, the mass RCN is also equivariant to scales and aspect ratios. This is due to the warping and normalization behavior of the ROI align layer and also the pasteback behavior of the mask. And the scale equivariant behavior is also enhanced by the scale invariant features introduced by FPN. So, however, there are some cases where we don't want the equivariance. So for example, for the same pixel, if you evaluate in different ROIs, then it may have a different label because it can be a foreground in some ROI, but it can be a background in the other. So in the case of mass RCN, this is actually implicitly addressed by zero padding in the ROI boundary, which actually breaks the equivariance because if you pad 0, it is not fully convolutional before and after the ROIs. In this case, the outside objects are suppressed, and it is unlikely for the same pixel to have the same label if the two ROIs has a very large change. So this means in the mass RCN system, it is only equivariant to small change, to small local change of ROIs, which is actually a desired property in the problem of instance segmentation. So here is one example of the mass RCN result, which I feel impressive. If you see the person in the middle, it is surrounded by many other objects of the same category. But mass RCN can still do a very good job in this case. So next, I'm going to very briefly analyze the results of the mass RCN system. So in the first ablation experiment, I'm going to show the comparison between ROI pool and ROI align. And here I use a very extreme backbone, which has a stride of 32. And in this case, if we evaluate the AP of a very high IOU metric, then we can see that actually ROI align can improve the AP by 10 points in absolute, or actually 50% relative. And also, this entry has a very good bounding box AP, and it is just done in a feature map of a stride of 32 without any dilation or upsampling. So this demonstrate the importance of the ROI align layer. And also, on the other hand, we have tried to use a softmax layer to perform the mass prediction, or a sigmoid layer to perform the mass prediction. In the case of a softmax layer, the network is expected to predict, let's say, an 80 class label for every single pixel. In the case of sigmoid, it is just a binary classification to distinguish foreground and background in this case. So we found that if we use a sigmoid, the AP is much higher. So here is my explanation. Actually, in the case of mass RCN, the recognition problem has been done by the classification head. And the recognition problem, or in some sense, the classification problem, is an invariance problem. You just need an invariance label, so which a classification head can do a very good job. On the other hand, in the case of the mass head, actually you don't need to recognize again, and also you don't need the invariance representation. What you need is the equivariant representation. So in that case, actually the sigmoid representation, the binary foreground and background classification may give better results and also may simplify the task. And we have also tried to use an MLP head, which consists of a few of fully connected layers in comparison with the FCN head used by default in mass RCN. So we can see that the FCN head did a better job and it improved the AP by about 2.1%. So in my opinion, if you use an MLP head, actually you lose the place-coded information and it is too abstracted. This is just like I give you an apple and you can see it, but you cannot very precisely outline the label. So it is not exactly the original apple that is seen. But if you use the FCN head, it is translation equivariant, so it may do a better job in the pixel-to-pixel alignment instant segmentation task. So here is some systematic comparisons between mass RCN and many previous systems. So this is the result shown in the paper. Our method is about 2 AP better than the winner of last year, and our system can run in about 200 milliseconds per image. So our method can also naturally benefit from better features. And the mass RCN system can also improve object detection. For example, thanks to the ROI aligned behavior, it can improve AP by 1 point. And thanks to the multitask training, it can improve the box AP by another point. So we have improved the mass RCN result for the COCO competition. So without doing much beyond what we presented, we can achieve a mass RCN result of a single model of about 48% bounding box AP and 43.5 mass AP. And we will present more details in the COCO workshop. So here are some results, and I think I'm running out of time. I will skip it. Here is one result in Cityscape. This is one failure case. So we can see that the mass RCN can still fail if the objects are heavily occluded, and if there is some object missing, then it may predict some false mask. And also, recognition is still a very challenging problem, and in some of the cases, the objects are just not correctly recognized. I'm going to skip some of these technical details. And finally, I will talk about a very simple generalization of mask ASEAN for key point detection. Actually, we can think of one key point as a one hot mask, and then a human pose can just be categorized as, for example, a 17 key point mask. So in this case, we use softmax over the spatial localizations to encourage a one hot output in the case of mask ASEAN. And in the case of key point detection, actually, I would like to highlight that the entire system shares the same equivariance of the original mask ASEAN system. So it means that it is translation equivariance, it is kind of scale and aspect ratio equivariant. So here is one example, and here is one video which is just done by frame mask ASEAN, and there is no temporal smoothing. So basically, I think that's it. We are going to have 2 more presentations about mask ASEAN in this ICCV, and we will open source the code very soon in a platform called Detector proposed by Facebook AI Research. And that's it. Thank you. Yeah, I think we are running out of time, so I will take questions offline.
Did you do anything special? Looks right. Okay, so for the next 20 minutes or so, I will talk about recognizing human-object interactions. So both Ross and Kaming, I'm sure, have convinced you right now that there's been a lot of good progress made on object detection and instant segmentation, and they have explained how one can attack this problem. And not only for object detection and instant segmentation, but one can also, with very minor changes, tackle even more fine-grained tasks, such as pose estimation. And the great progress that we've seen so far is also and should be attributed to the really compelling and large-scale data sets that exist out there, such as MS-COCO, cityscapes, and so on. So let's focus on this image. So this shows a Nascar CNN output. You can see that there is some people detected, umbrellas, some cars in the background. However, if you look at this image can tell you a lot more than just what objects are present in it. For example, it can tell you that this person on the left is standing and is holding this umbrella on top. It will tell you that the person in the middle is also standing and is looking at the person on their left, on their right. So recognizing human-object interactions is extremely important because it's a one step closer to better understanding scenes. And of course, it will take advantage of all the nice progress made for object detection, because you still need to localize the objects, you need to localize the humans, and you also need to predict how they're interacting. And for this talk, we will focus on the human-object interactions, mostly because they are the most diverse set of interactions, but one could also study all type of interactions of objects by extending this work. So other than trying to understand scenes, human-object interactions can be directly used for many applications. One application that seems very relevant is the one of building cameras that will naturally attend to the object of interactions in, for example, instructional videos or cooking videos. Another one is the use of the detected interactions for better image descriptions or question answering. and also for video understanding. So moving forward, it's important when we tackle these tasks to actually build good data sets. So currently there's 2 publicly available data sets on human-object interactions. The first one is VCOCO. It's called Verbs in COCO. It consists of COCO images, which have been annotated with 26 types of interactions. There's about 10,000 images and 17,000 people instances. The interactions look something like carrying an object or eating an object with a tool like a knife. Or for example, standing, which don't involve an object of interaction, but are still an action that people do and is very descriptive. The other data set that is publicly available is called HeCoDet from Jia Deng's team. And this data set includes 600 types of interactions from almost 50,000 images. Here, the interactions look something like chasing a bird, or feeding a bird, or herding cows. So let's compare these 2 data sets. And this is important just for us to realize how different teams try to tackle these tasks and what kind of details are in those data sets that we could take advantage of. So when it comes to comparing VCOCO and HeCoDet, so the biggest difference is how they define the interaction. So in VCOCO, interaction is defined by a human interacting with an object, and the object type is not of importance. Well, in the HeCoDet data set, the interaction is object-specific. So holding an apple is considered a different interaction than holding an orange. In addition, their annotations have been collected in a much different way. For example, in VCOCO, they first annotated the objects and the people and then linked them together. Well, in the HeCoDet, the process was kind of opposite. And last but not least, if a person is not interacting with any object, in HeCoDet, this person is omitted. Well, in VCOCO, this person is annotated with a not interaction. So further on, how do we evaluate human-object interactions? So for object detection, we compute AP for every object separately. Here, we will also compute AP, but for every interaction. So what is important here is to understand how to define a true positive. So let's assume that we have a triplet prediction of a human instance, an object instance, and an interaction type. This prediction is going to be a true positive if the ground truth human and the predicted human overlap more than a threshold, in this case 0.5. If the detected object and the ground truth object also overlap for more than 0.5. And also if the predicted interaction is correct. And of course, the same thing with object detection, we penalize for duplicate predictions. So what are the challenges when it comes to solving human-object interactions? So one thing that we should all realize is that it's a joint detection and interaction recognition problem. One has to maintain the performance of object detection while also recognizing interactions. And there is a common misconception in the community that this is not quite true, since maybe person detection is solved. Well, that's not true, since COCO AP for people is definitely not 100%. What is more is that it's a fine-grained recognition problem. Also, there is a lot of uneven data distribution. We have a lot of long tails, and that is because some actions are way more frequent than others. And last but not least, the objects that we tend to interact are small. And this makes it challenging because detecting small object is a very difficult task. And without detecting them, there is no hope in solving this task at all. Okay, so there's been a lot of work already trying to tackle these tasks. And here is a list of potential publications. And we will post the slides online so you can take a look at them offline. But I would like to focus on this really interesting line of work that has recently been blooming, the one of visual relationships. So the task of predicting visual relationships is the one of trying to link objects together with a predicate. These objects can be any object that you see in a scene, and the predicate can take many forms. It can be a verb, it can be an action, or it can be a spatial relationship, such as next to or under. And also it can be a preposition phrase, like drive on or sit on. So what are some key differences between detecting human-object interactions and visual relationships? So first of all is the task. For human-object interaction, we care about the humans, and we care about the verbs only. Visual relationships, the task is much more open, and the vocabulary is open. And this makes it very challenging, because first, the annotations that you can collect cannot be exhaustive. And the lack of exhaustive annotations cannot allow one to measure precision. So for visual relationships, people can only evaluate for recall. While for a closed-world human-object interaction task, both precision and recall should be evaluated. So for the rest of the talk, I will focus on one approach in which you can follow to attack this task. And I will start with some observations of the nature of the task and then propose what we believe is a very compelling way of solving this. So first and foremost, a person in an image can participate in many actions. These actions might or might not involve any objects. For example, in this case, this person is standing, but also they're cutting with a knife. Second, and very important, the appearance of the instance and the action type are most revealing about the location of the object, even if you can't see it. So for example, in this case, the pose of the person and their appearance can be very indicative of where the object of interaction is located. And last but not least, in order to detect the object, you need to be able to have a mechanism to detect objects and images, such as Nascar CNN. So for this, we actually proposed InteractNet. InteractNet is a network. It's an end-to-end system that predicts human-object interaction and consists of 3 different branches. So the first branch is the object detection branch, which will predict objects and the object types. The second branch will take as input the detected human instances and will try to predict the action type as well as the relative location of the object of interaction. So on the figure here, we show what that exactly means. We parameterize the target location with the location of the center and the size of the box of the object of interaction. You can see that when you take as input the human box along with the features, one can precisely predict where the object of interaction could be located in the image, shown here with dashed line. And in this case, even if the object of interaction is outside of the box of the person, so the system doesn't have any direct access to the visual features, it can still make a very reasonable prediction. And the last branch will take as input the human box as well as the objects, and will try to assign a confidence, try to assign a score of whether this pair can be a reasonable interaction pair for that action. So some details for those of you who care about the architecture. Our network consists of, the first part is an image-specific convolutional features. And in this case, we use a ResNet 50 FPN network, which has been very explicitly explained to you by Ross and Kai-Ming. The branches are nothing but a sequence of FC layers, each of which predict their own output. The object branch will predict the object types and the box regression parameters. The human-centric branch will predict the action types and also the object of interaction box parameters. And the interaction branch will predict, and again, the action scores. At inference, all these branches come together and become a team. First off, the object branch will predict a set of human boxes and a set of object boxes. The human-centric branch will take those human detections and will try to predict action types and relative object location, which will form the mean of a normal distribution. And the interaction branch will take the human detections and the object detections and will assign a confidence scores to those. And they all come together to score a triplet prediction by simply combining all those scores, confidences under the normal distribution. So let's dive into the results. I will present the results on the VCOCO dataset. So our baseline approach here, which only consists of detecting objects, assigning an action type to the humans, while assigning an object merely based on training statistics will give something like 31.8. Once you add the interaction branch, you get a very small improvement, which means that there is definitely some visual information when you process the objects as well. Well, when you add the target location, when you try to predict where the object is located based on the human features, you get a much bigger boost. This means that the appearance of the person is definitely a strong cue when predicting where the object is located. And when you bring everything together, you get a really nice boost, especially compared to the baseline of almost 8%. And so here are some results, some predictions on the VCOCO dataset showing the predicted interactions. You can see that you can detect interactions under very difficult circumstances, like in this case, where you can merely see a person. And what is very important to notice is that the task wants the model to make predictions in an exhaustive manner. You want to predict interaction, all the types of interaction a person is participating in. For example, in this case, the person on the right is holding a cup while sitting on a couch. And finally, I want to show some errors that our system is very prone on doing. These errors are mostly due to reasoning mistakes. For example, in this case, in the second image, you can see that a person is indeed drinking, but the object of interaction is not the one that is this person is holding, is the person that's holding next to it. Or in this case, this person is indeed holding a tennis racket, but it's not, the action prediction is not correct. We predicted that the person is hitting while the correct action is holding. Thank you very much. Yes. Okay, so regarding the first part of the question, which was what do you do with the long tails? So one thing that we have found, one thing that is definitely something that's doable is to actually weight your examples. So you can weight your positive examples based on how many of positive examples exist in the training set. Another thing is to sample your data so that you see the most infrequent classes more. So in your mini batches when you train your network. I don't remember, what's the second part of the question? These are two different interactions. The interactions are always directed. So this person will be doing one interaction, and then you have to predict also that the other person is receiving something. So that's another interaction. Yeah. Yes? Yeah, come over. I don't think I can hear anything. Yeah, it is definitely true that time action recognition makes a lot more sense when you have access to time and you can see a sequence of frames. Yet, you as a human can still recognize whether that person was hitting or not, because no, you couldn't. I agree. I agree with you that I think that we should also be studying this in videos and in time, but the challenges there are much different. I agree. Yeah, we can try to find, but I agree with your point. Yeah. Okay, welcome back. Next speaker is Zhifeng Dai, and he will be talking about flow-based video recognition.
Hi, everyone. I'm Zhifeng Dai from VC Group of MSIA. Today, I will talk our recent work on flow-based video recognition. This is joint work with Xizhou Zhu, Yuwen Xiong, Yujie Wang, Lu Yuan, and Yicheng Wei. So I will first give a brief introduction. Then I will introduce two of our recent works in this direction, and finally is a quick summary. Recent years have witnessed significant success of deep convolutional neural networks for image recognition. For example, image classification, semantic segmentation, and object detection. With their success, the recognition tasks have been extended from image domain to video domain. Fast and accurate video recognition is crucial for high-value scenarios. For example, autonomous driving and video surveillance. Nevertheless, applying existing image recognition networks on individual video frames is problematic. In terms of speed, it introduces unaffordable computational cost for most applications. Although state-of-the-art object detectors and semantic segmentation algorithms have been almost fully convolutional, the computation is still not efficient enough for real-time video recognition. In terms of accuracy, directly applying per-frame recognition methods for video is also challenging. The recognition accuracy suffers from deteriorated object appearance in videos, which are seldom observed in still images, such as motion blur, video defocus, real poses, as shown here. It is widely recognized that image content varies slowly over video frames. Such data redundancy and continuity can be modeled by motion or to see by optical flow. Here we developed flow-based video recognition methods. The key idea is that flow can be applied to propagate feature maps across frames, and a flow estimation network can be trained driven by the ultimate recognition task in an end-to-end fashion. Based on the idea, we developed a clean end-to-end
and general methods for improving video recognition speed and accuracy. Such methods have powered the winning entry of this year's ImageNet VID challenge. Okay, let's come to our first work called the Deep Feature Flow for Video Recognition. Modern SIEM-based image recognition network shares a similar structure. A deep convolutional subnetwork, NFIT, is applied on the input image I to produce feature maps F on the whole image. Its layers are convolutional and account for the most computation. The internal convolutional feature maps have the same spatial extent of the input image, but usually at a smaller resolution, for example, 16 times smaller. They preserve the spatial correspondence between the low-level image content and the middle to high-level semantic concepts. A shallow task-specific subnetwork, NTask, is applied on the feature maps to generate the output. For example, 1 or 2 layers, fully collected layers for classification, or faster RFCN, this kind of things for detection, or 1 layer of convolution for semantic segmentation in a fully convolutional fashion. And as we discussed before, a lateral extension from image recognition to video to apply the image recognition network on each frame. It is computationally expensive, and the deep and expensive feature extraction network is applied on every frame. It takes the majority computational overhead for video recognition. The features in deep convolutional layers encode the semantic concepts and correspond to spatial locations in the image. Such correspondence provides us opportunities to cheaply propagate the features between nearby frames by spatial warping, similar to optical flow. As exemplified in the figure here, 2 intermediate feature maps are responsive to car and person concepts. The response patterns are similar on 2 nearby frames, but are at different spatial locations. After propagation by the flow field estimated on the 2 input frames, the propagated features can well approximate the original features. Motivated by this key idea, we present deep feature flow, a fast and accurate approach for video recognition. It applies an image recognition network on sparse keyframes, for example, every 5 frames or every 10 frames. It propagates the deep feature maps from the keyframe to other frames via a flow field. Typically, the flow field and for the flow estimation and the feature propagation operations are much cheaper than the computation of convolutional features. Thus, the computational bottleneck can be avoided and a significant speed up can be achieved. Then next come to the training. When the flow field is also estimated by a network, the entire architecture can be trained end-to-end with both image recognition and the flow networks optimized for the recognition task. In each mini-batch, a pair of nearby video frames are randomly sampled. By applying the forward pass, recognition results are predicted on both the keyframe and the current frame, which incurs a loss against the ground truth result. The loss error gradients are backpropagated throughout to update all the components. It is worth noting here that the feature warping is implemented via bilinear interpolation, and we can compute the derivation of the warped features with respect to both the input features and also the flow field. And it is also worth noting that there is no additional supervision to drive the training of the flow network. For each long key frame, the computational cost ratio of the proposed approach and the per frame baseline is as shown here. As the warping operation and the task-specific network can be computed very cheaply, the ratio can be approximated by the computational ratio of the flow network versus the feature extraction network. As we can see from the bottom table, the flow network is much cheaper than the feature extraction network. For example, the original flowlet network, its computation is just 1 out of 12 compared to ResNet 101. And this is also our default setting, our experiments. By utilizing the more modern architectures for flow estimation, here we hand-cooked a structure called a flowlet inception by borrowing the idea of inception network. Its computational cost can be like 100 times smaller than that of ResNet. So here, my understanding is that, my personal understanding is that the flow estimation problem can be a much easier problem compared to image recognition. For example, 20 years ago, we already have some flow estimation methods that work quite well and at a reasonable speed. However, for image recognition, it's still recently we have deep networks, then we have some very good results. So because the flow estimation problem is much simpler than image recognition, we can solve the problem or get good results at the cost of much lower computational overhead. That's my understanding of this table here. Okay, and we did extensive experiments of video recognition on 2 data sets. Yeah, that's the best data sets we could have till now, yeah. And yeah, much better data sets would definitely be a power engine for the research of video recognition. For semantic segmentation, we did experiments on the cityscapes data set. It has a very low frame rate. And for object detection, we did experiments on embedded VID. It has a higher frame rate. And for the key frame choice strategy, here we just applied a very simple strategy that is a fixed every 5 or every 10 frames, we choose a key frame. And yeah, that's the experiment setting. We first did ablation study on both the cityscapes and the image-led VID dataset for segmentation and detection, respectively. First, let's look at the overall results. Compared to the per frame baseline, our proposed deep feature flow method, it can achieve 4 to 5 times speed up at a very low cost, in very low trade-off in terms of accuracy. And we have also tried to just incorporate state-of-the-art flow estimation methods, no matter it's a handcrafted flow or some deeply nerd flow. We just use a recognition network trained on each image and the flow estimation method that is handcrafted or pre-trained. They are state-of-the-art flow estimation methods. The results are much worse than our proposed deep feature flow method. And we hypothesize that this is because the end-to-end training can fine-tune the entire architecture for the ultimate task of video recognition. So we also did more ablation study that is basically fix the feature extraction network in our deep feature flow, that is DFF fix N, or fix the flow estimation network, just utilize the state-of-the-art pre-trained flow network without fine-tuning for the task of video recognition. The accuracy can be much worse than the ultimate system of end-to-end trained deep feature flow network. So basically, the conclusion is that joint end-to-end training is effective for this task. And we further did experiments about the accuracy, speed-up trade-off by using different networks and by varying the duration length of the keyframe. Here, different curves correspond to different combinations of the feature extraction network. We utilized ResNet 15 layers and 101, and we tried different flow network, flowlet, and some variations with even lower computational overhead. And the X-ray shows the speed, basically FPS, runtime speed, and the y-axis corresponds to the accuracy, MAP score. We can adjust, we can pick point on a curve by choosing a fixed duration length, keyframe duration length. Yeah. And the first conclusion is that when we can get significant speed up with decent accuracy drop, for example, 10 times faster than the pre-frame baseline at a cost of 4.4% accuracy drop. The second thing we can conclude from this figure is that how can we choose a flow function? And we found that the cheapest flow let inception is the best when we want to run it really fast at a high frame rate. And how to choose the convolutional features? We can utilize the more expensive Resident 101 compared to Resident 15 layers. Yeah, so basically, the deep feature flow, you can utilize very cheap flow network to get highest accuracy speed of trade-off, good trade-off. Yeah, that's a basic conclusion. Here are some visual results shown here. This is semantic segmentation on the cityscape dataset. Here are the results on the ImageNet VID dataset. Here we specially choose some samples correspond to different challenging scenarios. So the proposed method worked reasonably well on these challenging scenarios. Okay, I will quickly introduce our next work that is called flow-guided feature aggregation for video object detection. Directly applying image recognition methods for video recognition is also challenging because the recognition accuracy suffers from the deteriorated appearance. Such deterioration are seldomly observed in still images. As quantified in our experiments, a state-of-the-art still image object detector based on RFCN and Resident 101 deteriorates remarkably for fast-moving objects on videos. Nevertheless, the video has rich information about the same object instance, usually observed in multiple snapshots in a short time. Such temporal information is exploited in existing video object detection methods in a simple way. These methods first apply object detector in single frames and then assemble the detected bounding boxes across temporal dimension in a dedicated post-processing step. This step relies on handcrafted bounding box association rules, such as object tracking. So in general, such methods are heuristic and heavily engineered, but they are widely used in competitions. And for our work, our motivation is that features matter as a success in image recognition. We try to enhance the deep features in the network by utilizing flow across multiple frames. It is a principled, clean baseline, and its problem is rarely studied. The proposed flow-guided feature aggregation method is illustrated here. The feature extraction network is applied on the individual frames to produce the per-frame feature maps. To enhance the feature at a reference frame, an optical flow field network estimates the motions between the nearby frames and the reference, and the features are warped with respect to the reference frame. And the warped features are finally aggregated according to an adaptive weighting network. And based on the aggregated feature maps, we produce the detection results. It is worth noting that compared with the box level methods, our approach works on the feature level and performs end-to-end training, and it is complementary to those box level techniques. And in experiments, we hand-cooked a motion IOU score to measure the object speed. So the existing metric of video object detection, it only counts a general MAP score over all the object instances. This is insufficient, especially considering that motion is the key property in video. So for better analysis, the ground objects are categorized according to their motion speed. And here, the figures here presents the histogram of motion IOU scores that we counted to measure the motion of the ground truth objects according to the scores, and we divide the objects in the dataset into slow, medium, and fast-moving groups, respectively. Here are the ablation study results. So we compared with different, with a single frame baseline and our methods and the different degenerated versions of our methods. The result is that suggests that all the components, flow adaptive weighting or end-to-end training, all these components are important. And the second conclusion is that our method is especially effective on fast-moving objects. It can be seen that the MAP scores improvement, the gap is much higher at the fast-moving objects, and the gap is much lower at the slow-moving object. This is, the result. And the drawback, the problem for the method, it is slower, as we need to do flow computation a lot of times on the other frames we want to aggregate. And so basically, this slide told us we should use more test frames for aggregation during testing. Borrowing more temporal features from different frames would be good. And we can just utilize 2 frames, randomly sample 2 nearby frames during training. It works reasonably good. Yeah, during training, we only have limited memory, so it's preferred that we use just 2 frames. And besides, the method can well integrate with the box level post-processing techniques. It can be shown in the figures here. There are different box level post-processing methods, MGP, tubelet rescoring, sequence NMS. Our proposed method is complementary with such methods. And it achieves good result. And it also powered the winning entry of this year's ImageLab VID challenge. We did not participate in the challenge. A third-party group participated and win the first place based on our clean, simple method. And here are some results, but I don't think I have time to show it. So I will just skip it, just show one example. Yeah. So by aggregating features, we can get better detection results on the frames, challenging frames. Okay, I will just skip it. As a summary, in our flow-guided video recognition method, we exploit motion for video recognition tasks. It can achieve faster speed or better accuracy. It is end-to-end and enabling joint learning of optical flow and recognition tasks. We did feature learning instead of a lot of heuristics, and it is general for different tasks. And we have put the code of the 2 papers on GitHub. Thank you for your time.
Any questions?
Oh, yeah. That's a good question. So basically the question is that the current strategy is that we sample keyframes at a fixed schedule, right? Every 5 or every 10 frames is a sample the keyframe. How can we guarantee that the sampled keyframes are useful, right? Yeah. So basically the answer is no. We cannot guarantee that. So basically, our focus of the paper is on how can we utilize the flow to propagate features across frames. So we just applied a very simple, or to say a very stupid rule for choosing the keyframe. And yeah, definitely you can do better by choosing the keyframe in an adaptive way according to the image content. Yes. Yeah. Thank you. I cannot hear. Delay. Okay. Okay. So I think your question is that whether there is delay for the proposed method, right? Yeah. I think the answer is yes. There would be a little bit delay for the proposed method because the runtime at the keyframe, it would be slower, and on the non-keyframe, it would be fast. So there will be a buffer time for us to processing the video stream. Yeah. I think this method, the proposed method, it can be best applied on the video analysis or video surveillance, this kind of task, which allows you a short time buffer. That would be the best scenario. Thanks a lot. Yeah. Okay.
This is yours?
Yeah, this is mine. Yeah.
Oh, okay.
Yeah. But he can use it if he wants.
Oh, it's okay. I think we got it.
Okay.
Oh, wait. You do it, and I introduce you. Okay, so next up, and our last speaker for today is Justin Johnson. He will talk today. The talk of the title is Beyond Object Instances. Yes, pray. I think it's good.
What's up?
That's not good.
That's interesting.
That's better. That's
You
new.
may need to adjust. You may need to adjust.
Is there a way to
resolution
adjust?
first.
Oh my God.
Resolution.
Really?
This does not.
What did you do?
Someone did something funny. I have no idea what the other is. You can choose scaled.
Yeah, true scale.
Maybe the other, not this one.
Oh my God.
Yes, choose this one.
If anyone is a true engineer, we need help. Yeah, okay,
All right, it looks like I'm an engineer. All right, sorry about the technical difficulty, but I'm Justin Johnson. I'm a PhD student at Stanford University, and hopefully I can get my laptop to work. All right, now we're finally in business. Okay, so I'm a PhD student at Stanford University, advised by Fei Li, and today I'll be talking about a lot of interesting tasks in computer vision that go beyond basic object detection. So when I look at some of these results coming out of recent papers like Nascar CNN, you start to wonder, is computer vision solved? Like, look at this. We're correctly identifying the table and the bottles and the chairs. We can get human poses. We can get everything. We can get almost everything that you could imagine from these images. Have Ross and Kaiming and Georgia and Piotr, is computer vision done? Should we all go home? I think personally that the answer is no. That even though we're starting to do really, really well on these instance level tasks like detection and segmentation, that there's still a whole host of new tasks that we can start to consider. And we can utilize this new technology that these new abilities to work with instances can enable whole new types of tasks that go far beyond basic object detection, recognition, other things like this. So through the course of this talk, I want to share with you some of the work of myself and others at Stanford that are about new tasks in computer vision that go beyond just object or instance level recognition. So one really great example from my lab mate Ranjay that demonstrates sort of the insufficiency of object detection alone is sort of here. So if you imagine we have two images, we know that in both images there's a llama in the left with a red bounding box and a person on the right with a green bounding box. You might think, based on the output of an object detector, that these two images are basically the same. But that isn't quite true. So for the one on the left, we see that there's a llama next to a person, which is about what you might expect here. But on the right, with nearly the exact same bounding boxes, we instead see a llama chasing a person, which is quite a semantically different thing than just the two objects standing next to each other. So this brings us to our first task beyond object detection, which we call visual relationship detection. Given an image, can we detect not only the objects that appear in the image, but also the semantic relationships that those objects are interacting with each other? So we had a paper at this ECCV that proposed a model to work on this new task of visual relationship detection. The way that this works is that on the left-hand side, we have a visual module that runs a region proposal method to determine where object-like regions in the image might appear, and then runs a classifier on each of these regions to try to guess the object category. On the right, we have a relationship detector that works on the union of bounding boxes from the region proposals and tries to classify what kind of semantic relationship these two objects are entering into. On the right-hand side, we have a separate language module that tries to guess, based on the linguistics of the triple, what is the sort of likelihood of this triple existing at all. So, for example, a man riding a horse might be a likely sort of triple, but a man riding an elephant might not be. And we can sort of use this as a prior to bias the probability that one of these triples will be detected in the image. So when we combine the visual module and this language module together, we get a model that can allow us to detect relationships in images. When we look at some of the results of this model on a test image, it gives you a sense for kind of the richness that visual relationship detection can give you in images. So for example, the model outputs that there's a person left of a person, which shows you that relationships can be spatial in nature. We also see that the one person is taller than the other person, which shows you that these relationships might be comparative, that tell you something about the magnitude of attributes of objects. This example also shows you that relationships can be asymmetric, that the directionality matters in these relationships, that the woman is taller than the child, not the other way around, and there's this other relationship with this other edge going the other direction between them. These relationships can also be verbs, with the person wearing the shirt or the person wearing the ski. You might also say that the person is standing on the snow or that the woman is helping the child. These relationships might also be prepositional. For example, the person is on the snow. And now when we put all of these things together, we see that relationships, taken one at a time, can be combined to form this generic, what we call a scene graph representation of the image. So here we've got a bunch of objects detected, but we've also identified a whole host of semantic relationships between objects, which allows us to represent the image now as this rich graph-based structure, which we think is a very powerful representation for images. To support this idea of a scene graph-based data set, to support this idea of scene graphs, we've actually worked on a new data set that builds scene graphs directly into the data set itself. So when you look at something like ImageNet, we're all familiar with this by now. Here we see a prototypical ImageNet example. We'll see an image together with maybe one object category. When we move to something like Coco, now in addition to one object category, we had a whole bunch of detected objects together with their bounding boxes. And now in our new data set called Visual Genome, we provide scene graph annotations for images, where not only are the individual objects annotated and localized, but we also have human-written semantic relationships between objects. And as you can see from this example from the data set here, these scene graphs can be very rich and capture a whole lot of information about the image. So this is probably, the font is probably a little bit too small for you to see here, but it says things like, man has a jacket, the jacket is turquoise, the man is wearing a cap, just et cetera, et cetera. It gives you a ton of detail about the images. So in total, the Visual Genome data set has about 108,000 images with 4.2 million region-level image descriptions. We have visual question answers. We have 1.4 million objects, 1.5 million of these semantic relationships to form scene graphs. We also provide annotated attributes for the objects. And the idea behind the Visual Genome data set is to try to provide something that goes beyond just beyond objects and beyond nouns, and provide these rich graph-based annotations that can enable much more interesting tasks. So as an example of an end task which can be made much more interesting with the introduction of scene graphs, we can think about something like image retrieval. So if we go on Google Images and we search for a man wearing a suit, it works pretty well. We get man wearing suits. If we instead search for a cute dog, well, people love to post pictures of their pets, so we obviously get a bunch of really cute dogs. But now things get interesting when the query gets more complex. If we instead search for a man wearing a suit holding a cute dog, now things don't work quite so well. We still get men wearing suits, we still get cute dogs, we get a man next to a cute dog, and we even get a dog wearing a suit, but we don't get any examples of a man wearing a suit holding a cute dog. Somehow, in whatever algorithm Google Images it's using, it's not really aware of the underlying graph structure of this query, and it does not respect all the relationships between the objects. So to get around this, a couple years ago in CVPR, we had a paper that tried to do image retrieval using the inherent graph-based structure of the query. So if we search for something like, when we incorporate only the objects in the query, we can get maybe a bench or a man on a bench. When we incorporate the attributes, we could specify that the man is sitting and get sort of a more rich control over the results. Or if we additionally specify that the man is sitting and the man is on the bench, now we get a much more fine-grained control over the types of images that we retrieve. We can also retrieve cats. So with these scene graphs, so the idea here is that now our query, instead of being a simple text string, our query is indeed this rich graph-based structure. And as we've already seen, these scene graphs can encode a whole ton of information about the images that we'd like to encode. So I don't expect you to read this graph here on the right because it has a lot of nodes and objects and whatnot, but I've summarized this information in a paragraph of text here on the left. So what this graph is basically asking for is an old sitting woman with gray hair, wearing glasses on her face, and wearing an open yellow jacket. We want the glasses to be below the blah, blah, blah. There's a lot of stuff going on in this query. And the idea, the model here is basically trying to ground the objects in the graph into regions in the image, and then have some binary potentials to ensure that the relationships in the graph are adhered to as well. So what we end up with is being able to take this scene graph query and then rank a whole set of images by the amount by which they match the scene graph query. And if we look at the top retrieval result for this query, we see that we indeed retrieve this image that contains all of this information, and all the objects have been grounded into regions in the image. So now we've seen that one interesting use for scene graphs is to start with a scene graph and use it to retrieve an image. But we can actually go the other way around as well and start with an image and then try to produce a scene graph that describes that image. So my lab mate Danfei Xu had a paper at CVPR this year that does scene graph generation via iterative message passing. So the idea is that we'll take an input image, get some proposals to try to guess at where the objects might be, and then do some joint graph inference to try to reason jointly about all of the object identities as well as all of the relationships between the objects. And then at the output, we end up producing this whole joint scene graph that describes the input image. And the way that this works is via an iterative message passing approach. So after we get some initial guess for what all the objects should be, then we need to predict a couple things. For each object, we need to predict an object category, and then between every pair of objects, we need to predict a semantic relationship, or possibly the null relationship, indicating that nothing is there. So the way that this works is that we have a network which works natively over the graph structure and passes messages along the edges using a GRU. And at the end of the day, we end up producing this scene graph representation. So this ends up allowing us to input an image and then output a scene graph describing the image. And as you can see, this ends up predicting things like a tree near a building, umbrella behind the man, a man holding the umbrella, which gives us this very rich representation of the scene. So this is sort of one interesting thing we can do beyond object detection, is working directly with scene graphs. And the visual genome data set has supported several different interesting things with scene graphs, including scene graph prediction and image retrieval. But let's step back here for a minute and think about what's going on. So if we start with an image and we use something like object detection, then we've gotten all the bounding boxes and object categories that appear in the image. But this is really not the end of the story. There's always going to be some end task that we want to perform based on the outputs of this object detector. And the paradigm with scene graphs is somewhat the same, where we've made the intermediate representation more complex, but we're still hoping that this intermediate scene graph will be useful for our end representation. So to make this a little bit more concrete, one of these end tasks that I like to think about is image description. So suppose we wanted to describe this image in natural language. Then we might hope that this scene graph gives us a rich enough intermediate representation to allow for the description based solely on the scene graph representation. But I think that doesn't quite turn out to be the case. Because if you look at this example description of two men playing with a red frisbee in the backyard near a boy and his bicycle, we see that some of the stuff we want to use to describe this image did not appear in the scene graph. And this is kind of an inherent problem with any kind of intermediate representation we might use in computer vision, that the end task we want to perform might not have, the intermediate representation might not always have the information we need to perform whatever end task we want. And this motivates the idea of end-to-end learning. Maybe instead what we should do is take our input image and then directly learn a mapping to whatever output we want to perform in an end-to-end fashion. But the trick here is now to perform this end-to-end learning in a way that still respects the underlying structure of the problem. So one example here is for image captioning that we saw at CVPR 15, where if we want to take an image and then write a sentence describing it, we can write down a single differentiable function that inputs an image, passes it through a convolutional network, and then uses a recurrent network to produce an image description one word at a time. And now because this is one joint end-to-end model, we can train this thing on our data set and then hopefully have a joint model that is not bottlenecked through any intermediate representations and can just do the end task that we care about. And when we train this thing up on the COCO data set, sometimes we see it produce really interesting results. We see that it describes this as a construction worker in an orange vest working on a road, which is basically correct. It says things like a man in a black shirt is playing a guitar, which is basically correct. But some of the responses that this model gives you makes you start to question its intelligence a little bit and makes you wonder, is it really understanding the semantics of the scene? Is it really looking at the individual object instances? Or is it instead just kind of looking at a global gist of the scene? So sometimes it says things like toilet with a seat up in a bathroom, but there's no toilet. Or sometimes it says things like a horse is standing in the middle of the road, but there's no horse. So there's something wrong with this model. It sort of fakes it. It makes it seem like it's working, but it's not really actually understanding all of the object instances and their relationships and all of the richness of these visual scenes. So one way we might fix this is to move away from this raw image captioning task and instead move to a new task that we call dense image captioning. So here, rather than producing a single unified description of the scene, instead, we want to localize regions of interest in the image, and then for each of these regions of interest, write a descriptive phrase. And here, it's going to be harder to fool us, because in addition to writing these bits of text, the model will also have to ground these bits of text in the image. So now we'll actually know whether it's looking at the right instances or not. And the way that this model works is really inspired by object detection. So we take the input image, pass it through a CNN, then use a region proposal network, very similar to faster RCNN or mask RCNN, where we propose regions off these intermediate features, do some differentiable cropping, and then feed each of these resulting feature vectors to a couple of fully connected layers and a recurrent neural network, which will then produce these image descriptions per region. And then we can train, because again, this is an end-to-end differentiable model, we can train the whole thing jointly. And in particular, we train on the visual genome data set, which in addition to scene graphs, also provides these region-level image descriptions written by humans. So after we train the model on the visual genome data set, we can run it on one of the test set images and see what kinds of things it says. So here it says things like a man riding an elephant, so it's aware of relationships. It's aware of two people sitting on a bench. It knows about object parts, so it knows about the head of elephant, trunk of elephant, leg of an elephant. Also background things like tree trunks. So one thing kind of interesting here is that because the model is jointly trained, it learns to localize the regions of interest that are important from the training data. So things like the elephant's arm and the elephant's head would not have been detected by objects given an object detector. But because these types of regions appear as ground truth annotated regions in the data set, the model learns to recognize these regions of interest through the joint training process. We can also have some fun by running the model on some of my collaborators at Stanford. It says things like black computer monitor on a desk, man wearing a blue shirt sitting on a chair, two people in the background, which is interesting because now we're localizing not individual objects, but sometimes pairs of objects and describing them all as a pair. Red and brown chair, sort of got it right. Also says interesting things like wall is white, where it describes these stuff regions in the background. So this dense captioning task is really giving us a lot of rich information about the scene, but somehow we've lost the compactness and the succinctness of these individual image captioning tasks. Now it seems that, now by looking at these, we're pretty convinced that the model is indeed learning to localize instances and reason about these instances, but this output of this dense captioning output seems a little bit unwieldy to use and to work with. And we might actually want something a little bit more compact if we're to apply this in a real setting. So that brings us to this other paper that we presented at this CVPR, which moves from dense captioning to paragraph level description. So here the idea is that we want to input an image and then output an entire descriptive paragraph of the image, rather than these succinct single sentence snippets that we saw earlier. But the way that we're going to do this is going to be informed by the dense captioning model, and it's going to explicitly reason hierarchically about the image by detecting regions, and hierarchically about the language side as well. So we'll take the input image, run it through a region detector, which had been trained for the dense captioning task, which then detects a lot of these regions of interest, and now we get a feature vector for each of these regions of interest, pool them together, and pass it to a hierarchical language model. The hierarchical language model has two layers. The first layer is a sentence RNN, which is responsible for predicting the number of sentences that we'll predict, as well as producing a topic vector to provide the content for each of the sentences that we generate. Each of these topic sentences then gets passed to a word level RNN, which is responsible for spitting out the words of that sentence one at a time. So then we end up generating these whole paragraphs. When we look at some of the example results from this model, we see that it's it's describing individual instances from the model, but it's also giving a more coherent long-form description of the image. So if we look at the left, we see there are two buses driving on the road. There's a yellow bus on the road with lines painted on it. It is stopped at the bus stop and a person is passing by. In front of the bus, there is a black and white bus. So it's not all correct, but we're sort of moving in this interesting direction of providing these really rich long-form descriptions of images informed by the instances that appear in the image. Another cool thing we can do with this model is interpret why it's producing the sentences that it is by looking at the regions that it detects in the image. So if we look at the example in the upper right, we see that it knows that this is an image of a baseball game. The batter is wearing a white uniform with black lettering and a red helmet. The batter is wearing a white uniform with black lettering and a red helmet. Oops, it repeated itself. The catcher is wearing a red helmet and red shirts and black pants. The catcher is wearing a red shirt and gray pants. The field is brown dirt and the grass is green. So it said a lot of stuff, some of which was true and some of which wasn't. But one interesting thing about this description is that it didn't talk about the pitcher at all. it only talked about the batter and the catcher. But if we look into the image and look at the regions that the model detected, we see that none of the detected regions captured the pitcher. So now it makes sense that the description will not talk about the pitcher because the model didn't detect it. But so now all of these tasks that we've seen so far are in this realm of perception, where we're going to take an input image and then produce some output which sort of describes something about the input image. But even within the realm of perception, there's a lot of things we can do. We saw object detection, we saw relationship detection, scene graph generation, retrieval, captioning, dense captioning. But there's a lot of tasks we can consider beyond raw perceptual tasks as well. Instead, we might want our model to look at the input image, perceive the visual information, and then reason somehow over that perceived visual information to perform some interesting task. And this is really not a new idea. This sort of harkens back to the very beginnings of AI. And if we look at Terry Winograd's PhD thesis back in 1971, he was already thinking about visual reasoning tasks. So he proposed a method called Sherdlu, wherein a human interacts with a machine to do very interesting things where the robot can manipulate this blocks world. So as an example interaction between the human and the machine, the human might say something like, the blue pyramid is nice, I like blocks which are not red, but I don't like anything which supports a pyramid. Do I like the gray box? That's a little bit non-trivial. Now the machine will then say no because it supports a pyramid. So I don't expect you to work through this example in your head right now, but the idea here is that the machine needs to do something beyond simply perceiving the visual scene. In addition to perceiving the objects in the scene, it also needs to think about these logical rules that the human has set forth and do some kind of reasoning over the visual information that it has extracted to now perform some interesting end task. Now at CVPR last year, at this CVPR, me and my collaborators at Facebook and Stanford introduced the Clever dataset to try to bring this idea of visual reasoning into the modern deep learning era. So in the Clever dataset, we provide these high quality rendered synthetic scenes of blocks and spheres and cylinders together with questions. And the model needs to look at the scene and try to answer the question based on the visual perception of the scene. So for this example question, we ask, how many spheres are left of the big sphere and the same color as the small rubber cylinder? So these questions, as you can see, can be kind of tricky with many different subparts. So we'll kind of walk through the reasoning of this one question. So we asked about the big sphere. So the big sphere is here. If we want to know about the spheres left of the big sphere, well, that's these two guys. Now, setting that aside, we then have to look for the small rubber cylinder, which is here. Next, we have to look for spheres which are the same color as the small rubber cylinder, which are over here. And now, finally, we need to combine these two intermediate results using the AND predicate and give us our final answer of 1. So what you can see is that from this type of example question, we're testing many different aspects of visual reasoning, including attribute identification, counting, comparison, spatial relations, and logical operations. Now, in addition to providing so we've already seen that the Clever dataset provides these rendered images and these natural language questions. But in addition, it also provides structured representations on both the visual side and the language side. On the image side, we provide a scene graph, which gives us the ground truth attributes and relationships between all the objects. And on the question side, we provide a functional program, which is this structured graph representation of the individual components of reasoning that need to be combined for answering the question. So in this example, we see that our functional program instructs us along one branch to filter for big objects, filter for spheres, ask for the material of the resulting object. Along the other branch, we need to filter for cubes, look to the right of whatever we found, look for the material of whatever we found in the previous step, and then finally compare these two materials to ask if they're the same. But the models don't have access to this. So because this task is actually pretty complex and pretty rich and compositional, a lot of standard deep learning systems don't work that well on this task. So for example, we tested a couple baseline models, including an LSTM that just looks at the question, a ResNet plus an LSTM that combined with some fully connected layers to try to answer these questions, and an attention-based model that uses an LSTM together with some spatial attention over the image. And what we see is that when we train these models on the Clever dataset, they perform quite a bit under human performance. the highest performing of these models only hits about 73% overall accuracy on the Clever data set, which, given the synthetic rendered nature of the visual scenes, is a little bit surprising. You might expect one of these powerful deep learning models to just do really, really well on this kind of data set. But what's interesting is that Clever allows us to dive deeper than just the overall accuracy and use the functional programs and the scene graph representations to try to understand where models are working and where models are not working. As one example, we can look at the accuracy of models on different types of questions. And what stands out here is that all of these models struggle on questions that ask them to compare attributes. So something like, is the cube the same color as the sphere? Models do pretty poorly on this type of question. But models are pretty good at simply identifying attributes of objects. So when we ask things like, what color is the cube next to the sphere, models are performing quite well. So clearly there's something going on strangely here, because our models are able to correctly identify the visual attributes of objects in the scene, but somehow they are unable to compare attributes of multiple objects in the scene simultaneously. So that means that there's something wrong with our models. So what I think we need to solve this problem is a compositional model for visual reasoning. These sort of traditional feed-forward convolutional network models don't have any inherent compositionality in the scene. We need something that can sort of reason independently about different types that can work on these can learn functions for these different basic operations and then combine them together in new ways to answer all these complex questions. So to this end, in a paper at this ICCV, we introduce a new model for visual reasoning that works on the Clever data set. So this model consists of two components. The first is a program generator, which reads the text of the question and outputs a program that will be used to answer the question. The second component is an execution engine that inputs the program and the image and then executes that program on the image as a sort of a visual program and outputs the answer to the question. Internally, the program generator consists of a sequence-to-sequence model that uses an LSTM to encode the question one word at a time, and then a second LSTM to output the program one functional node at a time. One thing to point out is that our programs can be tree structured, but the LSTM needs to output a sequence. So we simply have the LSTM output a prefix traversal of the program. The execution engine, on the other hand, is a neural module network, which is a sort of interesting model proposed by Andreas et al. At CVPR 16. So this module network consists of a number of modules, one module for each program in the functional programming language. And internally, each of these modules is just a little tiny neural network chunk. In particular, it's just a little tiny residual block with two convolutional layers and a residual connection. Now, given the program and given this module inventory, we're going to copy the program over and then assemble from the modules a custom neural network that mirrors the structure of the predicted program. In this way, we end up using a custom neural network architecture for each different type of program that our model might predict. In this way, our model is inherently compositional and can hopefully work much better on these complex, clever questions. We train this thing in 3 stages. First, we train the program generator in a supervised regime because it's just a sequence-to-sequence model. So here we can train this on question program pairs from the Clever data set. Next, in the second stage, we freeze the program generator and now train the execution engine using questions, predicted programs, and images and answers. And then in the final stage, we can use joint fine-tuning to jointly update both parts of the model. But there's a problem here. The program is this discrete structure that was predicted via sampling inside the program generator. So we can't really backpropagate through these sampling steps. The solution is to use the reinforce algorithm to compute a policy gradient directly from the predicted answer. And once we introduce reinforce, it allows us to jointly train this model even when we don't have any ground truth programs. When we look at the accuracy of this model on the Clever data set, we see that we make a huge jump from 73 all the way up to 97% accuracy. But there's a problem here. This 97% accuracy was using a lot of supervision. This was using annotated ground truth programs for every single question pair, for every single question in the Clever data set. But using 700,000 programs is kind of a lot of supervision. And we might hope that this model can do well using only a smaller amount of program supervision. So when we train the model using only 18,000 programs, which is a pretty small fraction of all those available, our accuracy only drops 2%, and still outperforms human workers on Mechanical Turk. When we use only 9,000 ground truth programs, our performance still outperforms all other models. So one thing we might hope this model can do is generalize to new data. Because it's learned this sort of inherently compositional approach to reasoning, we might hope that it can combine these different fundamental units of reasoning to answer new types of questions. But in this generalization process, we want to constrain to not use any ground truth programs, because these ground truth programs are this expensive structured type of data that we might not be able to get in real world scenarios. To this end, we collected a new data set called Clever Humans, where we asked people on Mechanical Turk to write questions about clever images. And they ask some pretty wild stuff, including about objects and their reflections in other objects, and they just really go wild on these images. So now when we take all of these models and we first train them on Clever and then test them on Clever Humans, we see that our model, trained with only 18,000 programs on Clever, does a little bit better than the baseline model. However, when we fine-tune all of the models on Clever Humans, our model gets a pretty huge jump in performance. But the really interesting thing here is that there are no ground truth programs available on Clever Humans. This massive jump in performance comes entirely through this joint fine-tuning process. We can introspect the performance of our model on the Clever Humans dataset by looking at the programs that it predicts on different types of questions. So for this question, it asks, is there a blue box in the items? And what's interesting is the words box and items never appear in the Clever dataset. So through this joint training process, the model learns to associate the word box with this question, with this program token for filtering for the shape of the object, and it needs to associate the word, it needs to figure out what to do with the word items, which it never saw before. But in this case, it can still infer the correct program. Sometimes it produces programs which are reasonable, but which don't really match the question. So here we ask, what shape is farthest right? The answer was cylinder. Now, the Clever dataset doesn't contain any things about absolute spatial position in the image. It only contains modules for relative spatial position. So the model tries to fake it by asking what is the color by looking for a blue cylinder, then looking to the right of that, and then looking for the shape. So it sort of faked this idea of absolute positioning using the relative positioning that it knows how to do. So in this case, that was sufficient for answering the question, but in general, this is not really the right semantics. And sometimes on complex questions, the model just totally fails and has no idea what kind of program to predict. I'd also like to point out some concurrent work in visual reasoning from Berkeley, which also appears at this ICCV, which proposes a very similar model for visual reasoning on the Clever dataset. And I'd suggest you check out their talk on Tuesday. There's also been a couple very recent papers on arXiv that work on the Clever dataset, the relational networks from DeepMind, which get a very, very strong performance using no ground truth programs whatsoever. And even more recently, the film model from Ethan Perez, which again uses no ground truth programs but still performs very well. So now there's some open questions in visual reasoning. One is, do we really need compositional reasoning at all? We've seen some of these models that perform very, very well on Clever using no ground truth programs, but it's unclear the degree to which they are actually reasoning compositionally versus just overfitting to the structure of questions in Clever. Another open question is, can we perform compositional reasoning without any program supervision whatsoever? I'm not sure. I think it'd be really cool. Another thing we need to learn how to do is run on real data. So far, we've only demonstrated this on this synthetic Clever benchmark, but we should really start thinking about real-world tasks that require compositional reasoning and see if we can get any of these ideas working there. So in summary, I've talked about a bunch of different new tasks that go beyond simple object detection. We talked about scene graphs that can be used for retrieval. We talked about language that can be used where we can describe images with joint training that utilizes the instance structure via dense captioning or via paragraph captioning. And we've also talked about this idea of visual reasoning, where we need to move beyond simply perceiving the things in the scene and try to instead combine what we see in the scene to work on more interesting reasoning problems. So I hope I've convinced you here that even though things like Nascar and CNN are producing these crazy results, there's still a lot of really interesting tasks we can do in computer vision. That's all I've got, and if you guys have any questions, I'd be happy to take them. Yeah, the question is, there's some stuff that we can see in the images that doesn't appear in the ground truth scene graphs, and what's up with that, basically. So that's something really interesting. Once we move to scene graphs, there's almost a nearly infinite amount of stuff that we could use to describe an image. You can imagine just sitting down and constructing this very complex scene graph about every possible thing you might imagine in the image. And to some extent, we've kind of punted on that so far by just, this is the data set, this is the ground truth scene graph. But I do agree we should probably think more carefully about what exactly should the ground truth scene graph contain. And that's a really good point. That's kind of a data problem.
So I think we're done for today. Unless there's any more questions, I will just say bye and thank you for coming. I hope you enjoyed it.